What we will study next is properties of a trees. So we have some propositions. A proposition is just like a result of a theorem, and to prove it is similar to prove a theorem. So we have these theorems and propositions. We would like to go over them. Let's go for the first one. The proposition says if we have two vertices in the tree, then there must be a unique simple path between them. We will prove this by contradiction. So we will write here proof, and we will write the contradiction statement. So we will say proof by contradiction. So what is the proof by contradiction? We start by the contradiction statement. It says suppose there are, if it is unique, then the negation statement that if we don't have a unique simple path. So suppose now there are minimum, suppose there are two different paths we will give the one P1, the label P1, and we will give the label for the second path P2 from V to W, because the question we have, it says that we have a simple path between V and W. So the contradiction statement, we assume that there are at least two different paths from P1 as a first path and P2 is the second path. The proof will work as follows as a draft. Imagine now this is the first vertex, which is V. The second vertex, let's say that this is W. Now, it says that suppose there are two different paths between these two vertices. So let us assume that the first path will come to a vertex, let's say L, and will go to W. This is P1. And assume we have P2 that goes in a different direction through K and will come back to W. So we have two different paths, this is now P2. So we have two different paths. The first one starts at a certain vertex, go all the way down until it reaches W. It will go through L. And the second path will go to other vertices through K and will also reach W. But if you start from V, you go through L, W, and come back to K and come back to V, then this will form a cycle. And you know that in trees we don't have cycles, which is a contradiction. So this is how we are going to prove the proposition. So we will say let P1 be the first path that will go from V, it will reach L, and then will reach W. And P2 as the second path will be also starting from V, will go through some vertices until it goes to K, and then goes to W. Then the path, now we have to go write it in reverse. Then the path V goes up to L, goes up to W, goes up to K, and goes back to V as a cycle, which is a contradiction. Why a contradiction? Because trees do not have cycles. So the first result we have from these properties is that between any two vertices in the tree, any simple path between them is unique. Now the second result as a property, it says a tree with n vertices has n minus 1 edges. So the relationship between edges and vertices is that if you know n, then you can find the number of edges which is equal to n minus 1. If I want to prove this statement, now notice that n is an integer controlling this statement. N can be from 1 and up. So 1 vertex, 2 vertices, 3 vertices, and etc. And since we have an integer that controls the statement, then we can prove it by induction. Let us first define the predicate of the statement or the theorem, and then we will use induction to prove it. So first we need to define the predicate, and we will say let Pn be the predicate a tree with n vertices has n minus 1 edges. This is similar to if and then, but it is expressed in a different way. Here the predicate says if we have a tree with n vertices, then it has n minus 1 edges. And notice that for n, it should start from 1. Otherwise, we will have negative number for the number of edges. So basis step. And when is the basis step? If n is equal to 1, so we need to prove that P1 is true. So we need to prove that the statement and when n is equal to 1 is true. Now notice when n is equal to 1, then what do we have? We have a tree with 1 vertex which has no edges. So what can we say here? Thus, when n is equal to 1, so when we have a tree with n equal to 1, has 1 minus 1, so we are applying the equation edges is it true? And in this case, P1 is it true? Now for the inductive step, so here we will write the inductive step. And in the inductive step, we will divide this step into 2 steps. First, we write our assumption, and then we write what is the induction. So for our assumption, what we are going to say? It says suppose, so here we will say assumption. So this is our assumption. And we will say, suppose Pk is it true when n is equal to k. So what is the statement that we are going to have? The statement that we are going to have for Pk, it will be a tree with k vertices has k minus 1 edges. And we call this statement, we call it the inductive hypothesis. For short, we write it as IH. Now for the induction, the one that we want to prove, the induction. And when this induction happens, it happens if n is equal to k plus 1. So we say we need to prove Pk plus 1. So we have to write Pk plus 1. So here we have Pk plus 1. And what does it say, pk plus 1? Simply remove k and put k plus 1. It says a tree with k plus 1 vertices. And now when you put for k plus 1 has k edges. And this is going to be our statement to be proved. And here I'll put question marks. That means this is the part that you need to prove for the induction. Let me explain theoretically how we are going to prove it, and then I will write the proof for you. The statement we want to prove is this. It says if we have a tree, with k plus 1 vertices, then it must have k edges. And how to prove this statement? Remember, we have IH. So you have to use the statement when n is equal to k in your proof. So how to prove it? Imagine we have the following tree. Just any tree with some vertices. And imagine now that this one is called tk plus 1. So it has how many vertices? It has tk plus 1. Now let us isolate one vertex. So let us just concentrate on this leaf and let us label it by, let's say, W, and its parent is V. Now if you want to remove this W from the tree, then how many edges you need to remove? You need to remove only one edge, which is this one. So when you remove W, now what is the tree that you are going to get? You are going to get another tree. Let me just use red color. Then you will have a tree that includes all vertices except W. And we are going to call it TK. Why we are going to call it TK? Because you have removed one vertex. So the original tree had k plus 1 vertices. When you removed one, then the resulting subtree consists of k vertices. Now if you go back to the induction hypothesis, what does it say here? It says a tree with k vertices, how many edges does it have? With k vertices, it has how many? It has k minus 1. So use this result in your proof. So if you go now to the red tree, for the red tree, let me use the red tree. For the red tree, then how many edges does it have? TK has k minus 1 edges. Now if I want to count number of edges for the whole tree, which is the one in green color, then simply take the number of edges for the red tree and add the edge the one that you have removed when you remove W. So k minus 1, and you add the edge, which is a plus 1. So you will get k, and this is what you need to prove at the end, that you need to prove that this tree has k edges. This is simply the proof. So I'm going to write the proof for you as it is explained by this picture. So suppose that a tree, and I'm going to label it TK plus 1, has k plus 1 vertices, and that W is a leaf of T, and let V be the parent of W. Now, when you remove the vertex, removing W from T and also the edge, WV, produces a tree, and I'm going to call it TK, with K vertices. Because if you remove only one vertex, then if it already has K plus 1 vertices, then if you remove one vertex and one edge also, then the number of vertices will reduce by 1 and we will have K vertices. Now by the induction hypothesis, hypothesis, which is IH, TK has K minus 1 edges. Hence, now we need to count the total number of edges of TK plus 1. Hence, the number of edges in TK plus 1, which is the original graph, is the number of edges in TK plus the removed edge, which is WV. So now we need to count. So that is, now in TK we have K minus 1 edges plus 1 edge that was removed. So here we have K edges, and this is the one we need to prove. Probably here I should put a note. Now this is for TK tree, and this one for the edge WV. And this completes the proof that for every tree with n vertices, it has n minus 1 edges.